Good morning, everybody, and welcome back to this series of talks, Cosmology, Lights and Shadows. Today we have Martín with a problem with the open questions and non-standard models. He's a little bit ill today, unfortunately, so he's going to speak from the chair. And, as we said yesterday, there were two speakers, actually, Miguel and Ricardo, that didn't finish their talks. So tomorrow we will gather again for the last part of the talks and also for some discussion. So.
Now? Yes. The last days we had some talks about cosmology, more from the standard point of view. And today I will speak about other possible views that there are in the literature. Of course, most of the cosmologists nowadays are in favor of the standard model, and the position that I will show here are defended by a minority of professional astrophysicists. But it is worth also to talk about this in order the people who want to approach to cosmology get an idea that there is some other ideas in the literature, not only the Big Bang. Even within the standard model, there is a wide range of positions. There are people who are defending that the standard model is strictly true in all the aspects. This is the absolute truth, and there is nothing to discuss. If we compare with the politics, we can call this the ultra-conservative people, the ultra-right. And then there are people who accept the standard model, basically, but still they are open to some discussions, and there may be some problems or whatever. I will move to the other side, to the progressive, or what you want to call, to the critical side, the people who are critical with the standard model, and also even that the people who propose different models. First of all, let's see. Today is not my day for the computer. Okay. Yeah. First of all, if it is the first time you approach to the cosmology, or even the second time, I think you should bear in mind this advice by Landau, the famous Russian physicist, that it was pronounced maybe 50 years ago, but it is still valid nowadays. Of course, the cosmology has advanced a lot in the last 50 years, but the position of the cosmologists is still the same. They still are totally sure, most of them, that there is no any problem with the model, so they are never in doubt. But in this, there are errors from time to time, and they are discovered. The model that we have nowadays, the concordance model, is not too old. The Big Bang is an old model. It comes from the 40s, maybe. But the concordance model is 12 years old. The concordance model, I mean, with the dark energy, the lambda CDM, and all these aspects. Previous to this model, there were other options. And with the time, it was demonstrated that these options were wrong. But in the 80s or in the 90s, the people defended this model with total security, without problem. For instance, the dark energy, the people defended that there was no dark energy, no cosmological constant. You can read a lot of papers in the 90s in which they claim with total security that the omega lambda is equal to 0, or the deceleration parameter in that was corresponded at that time. Of course, I have too little time to speak, and I will not touch all the ideas and all the critics to the Big Bang. For the observations, I just put this transparency, just giving some ideas which are in the literature, offering some open questions in astrophysics which have some direct or indirect relation to cosmology. Take it into account that I'm not defending these points. These are the points that I could find in the literature, so this does not represent my point of view. This is the point of view that one can read in the literature, which is critical with the standard model. If you want, we can discuss later about some of these points, but any of these points will take 1 hour. It's very complicated to discuss about this, so I will not recommend to enter in details of this, but perhaps a few questions we can discuss. For instance, one problem is that we have very high metallicity and thus at high redshift. This, in principle, with the assumptions of the standard model, is not expected because one expects a young population at high redshift, and one will expect close to 0 metallicity. Of course, there is an arrangement in which you can propose a very fast evolution of a very fast creation of metallicity, but in principle, this is not does not fit totally the expectations a priori of the model. We have very massive galaxies at high redshift. We know this is a problem because the hierarchical model, the standard model, predicts that the small masses, the galaxies with small masses are created first, and the massive galaxies are created later. So how can you have galaxies very massive at redshift 5, for instance? There is a problem of the string evolution of galaxy sizes, which, of course, you can relate it with the galaxy evolution itself, but it can also be related with cosmology. There is a problem with the helium in some galaxies, which is lower than the helium produces in the nucleosynthesis. The deuterium, the lithium, the beryllium, the helium-3 also has some failures with respect to the predictions. There are some inhomogeneities at scales larger than 200 megaparsecs. This can be observed with the recent surveys in the 2 mass or SLOAM. This is not expected by the standard model because at large scale we expect the universe should be homogeneous. There are observations or statistics of periodicity of redshift and correlations of objects of low and high redshift, which are not well understood. Possibly it has a solution, but still there are things we don't understand of that. There are flows of large-scale structure matter with too high velocity in comparison with the predictions of the model. The intergalactic matter temperature is more or less independent of the redshift. This is around 20,000 Kelvin, and this is not expected because if you are in a universe in expansion, you will expect some cooling of the intergalactic medium. The reionization epoch, this was discussed the previous days about the CMB. They give a number around redshift 10, more or less 10 or 11, is not in agreement with the reionization epoch derived from the quasar observations, which is around 6 or 7. There are several problems, minor or major problems, maybe they are minor, with the CMB, which are not expected, alignment of the quadrupole and the octopole, or some other effects which are perhaps not so important. We know that at present, the lambda CDM model does not work at galactic scales. There are several problems. So it works very well at large scale structure, predicting how the large scale structure performs. But when you want to measure the angular momentum of a galaxy or the distribution of the dark matter in the halo of the galaxies, this does not work very well at present. As said yesterday, the dark matter was not found yet. The density of clusters of galaxies is too high in comparison with the predictions of the model, which is also something that does not fit very well. And then there are theoretical considerations, not observational, which are not very clear. For instance, the origin of the dark energy, because there are some models in the particle physics related with the dark energy, but the difference in the order of magnitude of this energy is a factor 10 up to 120. This is totally incredible. So we don't know very well how to explain this dark energy without actual theory. Also, we don't observe antimatter, so we should observe some evidence for the CP violation, but we don't observe the CP violation also. There are not evidences. There are problems to understand inflation. That's some of the problems which I have read somewhere in the literature. So with this, I want to transmit the idea that, if you want to think that the standard model is perfect and explains everything, this is a position and you can respect, but one should bear in mind that there are still many small caveats, perhaps, or many things which are not very clear with the standard model. And any of these problems could be serious to modify significantly the model if we take it with.
Could you explain the periodicity of Z?
Yeah, this is an old problem. This was discovered in the 70s that both in the quasars and in the galaxies, if you take a histogram of the redshifts, you observe some periodicity. So there are some preferred values of the redshift. It is not random, the value of the redshift. This is not well understood in the standard model. And in the 70s, it was much discussed. Nowadays, still, I have seen some papers 2 years ago, 3 years ago, still some people discussing. There are people who claim that the statistic is well done, other people that criticize the statistics and they say, no, you have not taken into account this effect or whatever. But the fact is, it was a classical topic. The periodicity of redshift is this. The redshifts are not, there are preferred values of redshift. Yes.
No, because I don't want the idea that the public has the idea that many of those are real problems, in the sense that, so Martin has said that some people claim that there are problems, but the literature is plenty of people say that there's no problem at all. For example, massive galaxy high redshift. It is true that there is some massive galaxy high redshift, but their number is much more lower than what we find around. So it's clear that there is evolution in the number of massive galaxies with redshift, so that would imply, again, that there is something going on, so the galaxies are hierarchically assembling, and so the extreme evolution of galaxy sizes is well explained with the present models of lambda CDM. Periodicity of redshift, there's plenty of observation with the new surveys saying that there's nothing like those. So, of course, there are people claiming that there are problems, but I want also to point out that there are many people saying that there's many of those pointed in that list are not problem at all. So, yeah, just to point out.
Yes, as I said at the beginning, this does not reflect exactly my opinion. These are problems that are in the literature. For instance, about the massive galaxies, I have seen some plots in which you plot the prediction of the lambda CDM model, and you plot the observations, and there is a disagreement. But maybe you can explain in another way, possibly. Yes.
Martin, which ones, in your opinion, are the most serious problems to lambda matter? Which ones are the most challenging for lambda CDM?
Difficult to say. No, I cannot give you any solution. Always one has to wait many years. The discussion will not give you, the discussion of the problem will not give you the clue of what is the next step in the cosmology, the next change in the cosmology. You have to wait 10, 20 years. If some of these problems remain, and it's still a problem, then maybe we have to take it seriously. Or possibly it disappears, it vanishes because it is found that there is a systematic error or something like that. I cannot compromise my opinion in any of the problems. My opinion in general is that if a problem remains there for many tens of years and it is not solved, and people look at other sides when you talk about this problem, this is a problem. You have to solve all the problems. You cannot have any problem in the standard model. But I'm going just
to continue the discussion. So many of the problems listed there are related to properties of what we call the baryonic physics. So the complicated phase of the matter that we have, because dark matter, for example, is pressureless, so it's just gravity basically. So, and if you take a look to what the evidence has been shown in the last 3 days, so when we take a look to the large-scale structure where we think just gravity works, everything more or less works very nicely. So it's when you go to the scale of galaxies when the baryon physics start to have a role, because there is gas or there is dissipative, so it's much more complicated to model. Also, we have nuclear reaction forming the elements and so on. Then we have to see problems. But just to name that these problems are related to the cosmological model is, in my opinion, a step forward. So I think these are reflecting the complicated of the physics going on, which is much more than the gravity. So I just want to point out. But for example, from the list of open questions, I think that no dark matter found yet. If dark matter still is not seen in the next 10, 20 years, I would say that maybe we have to move on to another alternative. But just to have problems on the baryonic physics, I would not call it a challenge to the lambda CDM so far.
This is what I think too. We have to wait maybe 10, 20 years, and if after 20 years still dark matter is not found, maybe we have to think that it is a serious problem. Yes.
Well, since we are commenting on these problems or not problems, I would like to comment that nowadays about reionization. So I think that the common view now is that there is no contradiction between CMB and quasars, because what people think now is that reionization occurred during a long time, around between redshift 6 and 10 more or less. So it's what people think now is that it's a long period in which reionization is happening. Yeah, but when you say quasar is telling you redshift 6 and CMB redshift 10, you think, okay, there is something wrong here. But actually, the current model is that it's a period of time.
I think this I don't know, but you perhaps Ricardo can know that there is also a measurement of the thickness of the reionization epoch with the CMB also, not only the center of the epoch, but also the thickness. So there is also that. Well, we can discuss later. In principle, what I remember when I read some papers in the 90s or at the beginning of this decade, everybody was pretty sure that the reionization was at 6, and it was a short period. Now, with the CMB data, since they want to get an agreement, they have modified a little bit their position, and they say, no, the reionization epochs are too thicker. Yeah, this is also always the same problem, because we have a model in which we have to do so many things. So maybe I can mention parameters, but not only parameters. Any time in which you have a problem, you can say, well, the prediction was not this, but if I introduce a new thing, like the thickness of the reionization epoch or something new, the dark energy, dark matter, then I can solve the problem. And every time a new problem comes, a new solution comes ad hoc always. And this is the way not to get anything, not to get any conclusion, because you have to falsify the theory. You have to predict also. If you do a prediction and then the prediction is wrong, you have to admit, well, I was wrong. Maybe I have to modify, but no. Yeah, I know.
To transform from your framework to the observation. So of course, you say the reionization epoch took time at redshift 10. Then you go and you see that you have a process that went from redshift 6 to redshift 12, for example, a few hundred megayears, as I said. Okay, the guy that did the prediction saying it was a redshift 10 was totally okay. So that happened at that redshift. It doesn't happen at redshift 1 or at redshift 30, okay? But then when you move and want to compare with the astrophysical problem, you have to take into account that there's many physics going on there. So it's logical that it takes a time, for example. So the point I think we should discuss is whether our framework is correct or not. not when we compare it directly with particular specific astrophysical problems where we know the physics is complex.
Yeah,
That's
correct.
This is another point, no? That the land CDM is a statistical framework at the end. It predicts a statistical number of whatever, no? At a given epoch, no? But you cannot compare. It's not so fair, maybe, to compare particular cases to this land CDM statistical predictions. Probably.
I do not. In this, they do some prediction. For instance, the large scale structure. People, cosmologists are very proud that they can reproduce exactly the statistical properties of the large-scale structure. But then we have something like the density of cluster is too high. Then is it a perfect model or not? If the density of cluster is too high, then the prediction is wrong. Maybe you can modify something, but even from a statistical point of view, you have to admit that there is something that doesn't work. You can introduce some variation in the also, Ptolemaic astronomy was a framework. So you could introduce many epicycles on that, and it worked. Yeah.
Okay. It's a step forward to say, no, the physical problem is complicated, so then I have to change the framework. No. First, understand well the baryonic physics, which is really complicated. There is AGM feedback, there is dissipation, there's a lot of things. And then when you cannot solve this with normal physics, regular physics, then you can start considering that maybe your framework is wrong. But when your framework is giving you such a concordance with many different aspects, I would say, okay, it looks like a very nice tool for understanding things.
Yeah, but it is. Yes, this was the only transparency about the observation, because I'm not going to talk about it. My intention was here to talk about other theories that other people thought, well, maybe the Big Bang works better or not. I think it's not fair to say, well, when there is a successful prediction, this is a point in favor of Big Bang. When there is a non-successful prediction, this is that we have to change something in the baryonic. No. There are points in favor and points against. We have to be fair. The reason, well, maybe it's complicated, but the cosmological model is a picture of everything. You have to have a complete model for that. I'm going to talk about only two models. There are plenty of models in the literature, alternative models different from the Big Bang, but I have no time, and I will give some details of the two models, and then I will mention a list of other models. Perhaps the most famous one is the Quasi-steady State Cosmology, which previously it was called steady state cosmology without the quasi. And it was proposed in the 40s by Hoyle and other people at the same time that Big Bang was proposed. So it was a serious competitor. There is a change of philosophy with respect to the Big Bang. The frame, you would say, is different. They admit there is expansion of the universe, but there is not a Big Bang. There is not the universe is eternal, and it is always creating matter. There is not a creation of matter at the beginning of the universe, but the universe is always creating matter. The galaxies separate, and in the space which is in the galaxies, new matter arise continuously. So the aspect of the universe will be always the same, more or less. This is the reason to call it steady state. It is the image that we have of the universe is the same from any point of the universe, but also from any time. It does not change. This was the proposal. It is known that in the 50s there was a battle between both proposals, trying to be the better. Indeed, the steady state model was the first to propose the origin of the elements, both the heavy and the light elements. The Big Bang did it later. And the difference was that the steady state model proposes that the origin of both the heavy and the light elements comes from the stars. Everything is stellar nucleosynthesis, while the Big Bang assumes that the light elements were created in the beginning of the universe, the primordial nucleosynthesis. Perhaps the end or near end of this model came in the 60s, when there were some observations which favored clearly the Big Bang cosmology. For instance, it was known that at high redshift you have youngest galaxies. This could not be explained with this steady state cosmology. There were problems also with the radio sources distribution, with the quasar distribution, and the most important one was the discovery of the CMB radiation in 1965, which was clearly a point in favor of the standard model, because the standard model predicted clearly that there was a radiation with a black body shape and it was isotropic, as was explained in these days, and this was not predicted by the Quasi-steady state model. This was the step which moved the full community, I would say, practically all of them, to the Big Bang, and will make to forget the steady state cosmology. However, these people, Hoyle and other collaborators which came later, Barbich also was one of the first, but Narlikar was younger than them, created a modification of the model, taking into account these critics, and created what is called the quasi-steady state model in the 90s, the beginning of the 90s. So they had a problem, they could not observe the observations, and they said, let's go to modify our model in order to fit what we are observing. This is what everybody is doing. In this Big Bang cosmology is always doing this. When you cannot fit the anisotropies, you introduce the dark matter. When you cannot fit the supernova, you introduce the dark energy. But with the same philosophy, ad hoc, something which should not be done many times in science, but it is usually done. With the same philosophy, they have introduced something. They have introduced an oscillatory term. So the scale factor is not only apart from the exponential, which gives the expansion of the universe, is also oscillating, but never reach a value of 0. So there is not a Big Bang. Still, the model preserves the main characteristic in which they say that the universe is eternal, and there is a continuous creation of matter along the life of the universe. One important difference is also that now the creation of galaxies, the creation of matter that will give place to the galaxies, is places only in the minimum of this scale factor. No, never is 0. The minimum is here. You can see the plot is 2 or 3. There is no it never reaches a minimum value of 0. There is a minimum value, but it is not 0.
And the creation of the matter, is it supposed to be in some center of the universe? So there is like a sphere or something like that? The
creation of the matter is in this minimum, here, and it happens from time to time. Here we have some scale. Well, they have calculated the scales every many gigayears. So maybe.
No, I mean in the physical space.
No, everywhere. It happens everywhere, not in a place. No, it happens everywhere. So. This is not standard physics, of course. How can you create matter from nothing? You could ask. This was one of the main critics to this theory also from a theoretical point of view. This is something gratuitous, but has the same also level of indeed, yes, you are right. It is. But there is the important thing, and this is what the people fight to get, is that the universe is eternal. So this is an important difference. Yeah, yes, it's more. Yes, some people thought also that, and even they have related with religion. They have said Hoyle, for instance, was an atheist. Was not that he had no belief. However, the Big Bang defenders, many of them were closer to the Christianity and the idea of creation. So there is some background of philosophy there, but of course they don't talk about this philosophy in their paper. They just propose their model, and this is what the role of the scientist is, just propose some mathematical model, not to this kind of thing. But the principles are different, yes. Well, with this model, they were able to solve most of the main problems roughly. No, maybe not as good as the Big Bang, because these are 3 people, or the creators of this model. They are not thousands of people like in the Big Bang which are working in the model. But they could solve, for instance, you can observe younger galaxies at higher redshift. You can solve the radio source problem, the quasar distribution. Also, another element that they have introduced is also ad hoc was the origin of the CMB. They have to explain the origin of the CMB. So they have posited that there are some particles in the intergalactic medium which were not still observed. This is the problem. So there are no arguments in favor. These are called whiskers, are particles which are very long, and they can emit in perfect black body radiation. Yes, it's the same thing. They propose something. Let's assume that there is something that we cannot see, but it is there. You must believe that. Well, it is the same thing. I suppose the philosophy is the following. They have thought, if the people defending the Big Bang is doing that, why should not we do the same? The same thing.
But at the end, my point is that when you try to explain the nature, you came, at the end, you have the same ideas wherever you go. So at the end, I mean, if they refine this model, they will probably finish with the Big Bang, so with the lambda CDM, so in the dark energy, dark matters, because everything is in that direction.
Well, yeah, later I will talk about dark matter. They can explain also the anisotropies of the power spectrum. Here in this plot, you see in the dashed line is the Big Bang prediction in the 2007, and the solid line is their prediction. And the funny thing is that they only need 6 parameters too. So apparently it is not so difficult with 6 parameters to fit this. We have to bear in mind this is something that is not told many times when we speak about the power spectrum, that the positions of the peaks are not independent. They have some relation. So all the information that you see here is not independent. So it's possible with few parameters to look for some exotic cosmological model which fits more or less. But we have to say that at present the Big Bang model is better. For instance, you can see here that the third peak fits better, and even now with the refined model it is better. They also have introduced another element which I will not give many details here. They think that the redshift is due to the expansion, as I said, the cosmological redshift, but there is some part of the redshift which is intrinsic to the matter. And this is due to what they call variable mass hypothesis. They think that the mass of the protons and electrons is not a constant along the life of the universe. So it has changed. And due to this, the photons emitted by the protons in the past and the protons and the atoms in the past has a different redshift. This introduces some intrinsic redshift. I will not dedicate too much time to this. This has also been introduced ad hoc in order to explain the anomalies in the redshift that I have mentioned before, if there is such anomalies. So definitely, what we can say that roughly this model is able to explain many of the features which are explained by the standard model. Also, I have not mentioned the large-scale structure is also, there is a model of the creation of large-scale structure with this model, and it fits more or less. We know the refinement of the new simulations with the Big Bang model is much better. The Millennium simulation of that is the agreement is much better. But qualitatively, they are able to produce a model which explains most of the things. Of course, we have to bear in mind that the price to pay with this model is that you have introduced many things ad hoc. Rather than dark energy inflation and dark matter, you have introduced the whiskers, you have introduced the variable mass hypothesis, and you have introduced the oscillation also. But this is the game. The game is so. They have also several predictions different from the standard model, but as far as I know, nothing of this was tested because it is very difficult. They predict that there may be some blue shift at very faint galaxies, very difficult to measure at magnitude 27 to measure the spectrum of a galaxy. They predict that there may exist stars older than 14 gigayears from a previous population of stars. Remember that here the universe is eternal, and there may remain some rest of a previous population of the galaxy, but as far as we know, it was not found any star. And other things. This is a picture which was in the book by Hoyle, Barbich, and Narlica in the 20,000. It is a textbook, a serious book, published by the Cambridge University Press. And this has this funny thoughts about what they think about why people is following the Big Bang and not following our model or any other model. And they say, this is our view of the conformist approach to the standard hot Big Bang cosmology. We have resisted the temptation to name some of the leading issues. They say, well, people follow Big Bang because it is the fashion. The masses follow the leader. That is all. It's a sociological question. This is not very scientific. This is their thought. There is much to discuss here. Of course, there is science behind this. Well, how is the time? Let's see. Now I'm going to talk about other model, which was also quite important, and is still important because there are people working in this model. This is the plasma cosmology. One of the creators, perhaps the father of this model, was the Nobel Prize of Physics, Hannes Alfvén. And there are many disciples that have been working details of the model. The main idea that they have is that the gravity is a force in the universe. It is there, of course, there is no doubt. But the main force that regulates the formation of the galaxies and the structure is not the gravity, but the electromagnetic forces. There are intense electromagnetic forces. The universe is a plasma, it's ionized, and there are many currents with high velocity which can produce important electromagnetic forces. So they can produce the structure with these forces. This is something very important. The philosophy is important. We must bear in mind that since general relativity was proposed, cosmologists accepted without any doubt that the gravity is the important force. And everybody who is a cosmologist accepts that the general relativity is the frame to follow. But there are also other possible ideas. And this is one of the other possible ideas. These people are used to work in the laboratory with plasma, and they have realized that the filamentary structure which is observed in a plasma with some electromagnetic forces, which is down there, is very similar to the filamentary structure which is in the universe. So they have decided to create. Let's go to move the concepts of this plasma physics to the cosmology. Apparently it works. They have published some papers, not very cited, of course. Most of them are forgotten. Nobody knows them, but they are there. They can produce the filaments, the voids, the clusters, and so on, not with gravity, but with magnetic forces. Also, the formation of galaxies will be dominated by the electromagnetic forces, and they can explain the problem of the dark matter, many things with this thing. For the CMB, which is an obligatory topic if you want to talk about cosmology, of course, they have done something similar to what was done in the Quasi-steady State model. They have assumed that there is a particle in the intergalactic medium which thermalizes the radiation. The radiation, by the way, I have not mentioned, comes from the galaxies and stars. So the galaxies and stars emit a lot of radiation. This is absorbed and re-emitted with a much lower temperature and with a black body shape. According to them, according to their hypothesis, because this is not proved again, the absorption and re-emission by electrons in the intergalactic medium, the scattering of photons and electrons, can produce this black body radiation. They have some predictions, which, as far as I know, I think nobody has tested. About the expansion, there are two versions. In the 70s, Alfvén, first idea, they proposed that the expansion was real, and it was due to the repulsion between matter and antimatter. At that time, the antimatter was a fashion topic, so it could be believed. Nowadays, since no antimatter was observed, they have changed the version quite seriously in this, and they think that there is no expansion. The universe is static. Of course, you can say, what about the redshifts? But the redshifts are explained by other theories, what are called tidal light theories that I will mention now. But that's all. That is all I have to say about the plasma cosmology.
I think, is there a model, an eternal universe? Is it because you said there is no expansion, so it's like a static, eternal universe. Like
Also, yes, sure, eternal. Now, in all the versions, they assume that it is eternal. Either in the old version and the new version, it's also eternal universe. There is no big one. In this thing, they agree. About the redshift, together with the nucleosynthesis and the CMB, is perhaps the most important observational proof that topic that we have to treat in cosmology. There were some researches that expressed some doubt about the meaning of the redshift is expansion. Even the young Hubble, Edwin Hubble, expresses this doubt. He was, of course, the father of the idea of the expansion of the universe, but he has some doubt, and he says something. It seems likely that redshifts may not be due to an expanding universe. It's a possibility. So he was not saying that it is not, maybe. And much of the speculation on the structure of the universe may require examination. So this expresses that the feeling of that epoch, still in the 40s, that people had some doubts. Nowadays, I think most of the cosmologists have not any doubt about the expansion. The standard ones, at least. Already in the year 29, the same year of the Hubble's proposal of the Hubble law, which, by the way, nowadays is maybe you have read some discussion about which was the first to discover the expansion of the universe and the Hubble law. Apparently, it was Lemaitre in 1927, but this is another discussion that I'm not going to enter here. But in the 1929, there were also already other proposals apart from the expansion. The most significant one was this given by Zwicky, the same person of the dark matter, who proposes that indeed the universe was static, and what we are observing by the redshift of the galaxies is that the photons are losing their energy along its path, and this loss of energy is proportional to the travel, to the path. So with this, you can produce a Hubble law. The question is how to produce this loss of energy. In principle, Zwicky was convinced that it was due to some scattering. There was some scattering of the photons, interact with some matter which is in the way, and this produced some loss of energy. But soon, many critics arose, because most of the scatterings that we know produce some deviation of the straight path. Sorry. So the photons do not follow a straight line, but they are slightly deviated in their path. And this, if it is applied to the idea of redshift, will produce a blurring, in Spanish is emborronamiento, of the images of very distant galaxies. This is not observed. So when we observe a galaxy at a redshift 2, 3, 4, the image is quite neat, it's not any blurring. Also, most of the ways of scattering that we know depends on frequency, and what we see is that the redshift does not depend on the wavelength in which you observe. So these are the main critiques which were given to the idea of Zwicky. Nowadays, although we can say that most of the people do not discuss, most of the cosmologists do not even pay attention to this problem, there are still some theoretical physicists which are still searching for new ideas in this frame of the direct light. And they try to propose a frame in which they avoid these problems, dependent with frequency and the blurring. Here I mention, of course, what I have read in the literature. Do not ask me many details about this, because I'm not going to defend this model, just what I read, and what you can read somewhere, you find something. For instance, there is a proposal that the atoms in a state of 2s or 2p, this is an atomic state, can produce a scattering free of blurring. Also, what I have mentioned before, these people, Marmet, Greber, Brian Jolson, and others, have said that the interaction of photons with electrons could produce, they are theoretical ideas, they are not tested, could produce an appropriate direct light effect. The second line that I put, the first point is not very well tested. Indeed, there are not proofs, experimental proofs. The second point is well tested. people like Wolf, which is a high authority in optics, and other collaborators, they know very well that the redshift can be produced in some conditions, for instance, in a homogeneous and turbulent plasma. But this redshift still produces some blurring, so they have to solve this problem. If we go to very exotic ideas, of course, non-standard physics, we can imagine the interaction between the photons and vacuum excitations of an ether, a possible ether in the universe. Some nonlinear electrodynamics in photon propagations with the intergalactic magnetic fields. The interaction with wave packets of space-time curvature, or the interaction with gravitons. The photons have some interaction with gravitons, and this would produce also the scattering that we would need. Also, in terms of gravitation, there are some ideas. For instance, it is well known that there is a gravitational redshift. However, what is not easy is to apply it. In the context of the general relativity, with this you cannot explain the redshift of the galaxies. However, if you take another gravity scenario, different from general relativity, for instance, whale gravity, some people propose that this can explain the redshift of the galaxies. Here I give also other points related to gravity. There are different interpretations of gravity. Maybe one of the famous interpretation is the variable mass that I have mentioned before, related to the quasi-steady state model, in which if you suppose that the mass of the particles is not a constant, then the emitted photons intrinsically have an intrinsic redshift. There are people who think that the photon lose energy without any scattering, just automatically, spontaneously, it emits radiation, 3 Kelvin radiation, if you want to explain at the same time the CMB, and it is losing its energy along its path. There are people who think that the photon has mass. This is also an exotic theory. All of these ideas are away from the standard physics nowadays. I have to clarify. But it is good to know that there are ideas to explain the redshift, plenty of ideas. Yes.
Before you move to other topic, so one of the goals of the Extreme Large Telescope is to observe the expansion directly through the estimation of the change of the redshift with time of very distant galaxies. So this would be a project when the telescope is there. No?
I know. Yes.
But this would be a very interesting test to expansion, independent on any of. Because I agree with you that so far we cannot say redshift equal expansion, but I think this test will be really, really important for that.
Yes, sure. Well, with this idea in mind that the redshift can be explained by other mechanisms different from the Doppler or the cosmological. In this, Doppler effect and cosmological expansion are not the same thing, but are something similar. The question is that there is a recession of galaxies. If we admit that the recession of galaxies is not real and there are other mechanisms, then you can propose easily some static models. And there are plenty of literature that I will not discuss here, but there are also some people, I talk about professional physicists, not only amateur. Possibly all of us, we have received by email some proposals and amateur physicists proposing that the universe is static. No, I talk also that there are other where, because many of these proposals are very old, proposals that the universe is static and is compatible with general relativity and all that. Very exotic proposals. They have many problems, of course. This is the extreme. This is the other extreme of the Big Bang. The most different model that you can imagine is a model in which there is no expansion, the universe is eternal, and all the things that the Big Bang does not admit. There is something intermediate, more reasonable perhaps, that is admitting that the general background of the Big Bang, the main idea, is more or less correct, but we have to change some details. And this is, we can call variations on the standard model. For instance, already in the 30s, Milne proposes that instead of using general relativity, Einstein general relativity, we could explain more or less the same things with Newtonian cosmology. We know nowadays that this has some problems, but anyway, this is not the question. There are some proposals to accept the expansion, accept the main features of the Big Bang cosmology, but with different characteristics. For instance, about the problem of the inhomogeneity at large scale, some people propose that the cosmological principle is not correct, that the universe is homogeneous at large scale is not correct, and we can propose a fractal universe. There are proposals of a cold Big Bang, in which the temperature at the beginning of the universe is 0 instead of a very high or millions of Kelvin or whatever. Of course, then you have to explain the primordial nucleosynthesis in another way and the CMB in another way, but there are some proposals. There are proposals of the variations of the constants of physics to say that the speed of light, the gravity constant, and other constants are not indeed constant, but they change with time or distance. Many models of inflations, the old proposal, which is now not very fashioned, of strings and walls and other textures instead of inflation, to change the number of neutrino families, the amount of antimatter, etc. About the structure formation, nowadays the standard concordance model admits a hierarchical formation of the structure, but there are also people who defend a monolithic instead of hierarchical, that the largest galaxies are formed first. Well, nothing else about the cosmology in general. About some particular aspects like the dark matter, the non-baryonic dark matter, and the dark energy, there are also many proposals. I will give some examples within two particular observations. I will talk about the rotation curves, not about the clusters or not about the gravitational lensing, only rotation curves, and the supernova data for the dark energy. Here, for instance, I give 5 examples of proposals to explain the rotation curves without introducing the non-baryonic dark matter, the halo dark matter. Perhaps the best known is the modified gravity, the MOND or the MOG, or other gravitational theories. There are many of them. There is a proposal of a massive photon, that the photon has a very, very small mass, of course, undetectable, but it's not null. And if you take into account the mass of the photon, you have there the lost dark matter. There are proposals that the dark matter in the galaxies for the rotation curves is indeed baryonic, not non-baryonic. And they are, for instance, proposal that they are protons and alpha particles moving at relativistic speeds. So when they move at this speed, they do not interact with the matter, or very little, which is the requirement for the non-baryonic dark matter. Of course, you will say that this is hot dark matter. Of course, they are relativistic speeds. With this, you cannot explain the large-scale structure. But this is according to these people, they explain some things like the rotation curves and the gravitational lensing, and other problems maybe they have to do with other solutions. There are ideas like that the magnetic fields can explain the rotation curves, like Mataner's ideas, or that there is a dark matter, possibly non-baryonic or possibly baryonic, but it is not in the halo, but rather in the outer disk, and in some exotic form or not. These are some examples which propose some difference with the standard view of the non-baryonic dark matter in the rotation curves, I said. Some of these ideas can be translated to other scenarios of dark matter, but not all of them. About the supernova, the Hubble diagram, there are proposals like that the universe is inhomogeneous, and if you introduce this inhomogeneous universe, you don't need this dark matter element. You can explain this faint magnitude at redshift 1 or 1.5. Also some ideas that the luminosity of the supernova is not a constant, ideas related with extinction in the intergalactic medium, variation of C, G, and so on. Since I am finishing my time, and still will be interested to discuss something. My impression, there are plenty of ideas in the literature. Problems, of course, if the big one has problems, you can imagine that these ideas, which are not so developed, and possibly most of them are crazy ideas, have many more problems for all the basic topics, the expansion, the CMB, the light elements, and the large-scale structure. At present, the Big Bang model is the best model that we have, but it is not totally clear that at least from my opinion, that we have to be sure that this is the only model and all the rest we have to discard then. They have problems, but maybe they can be arranged in some way. Nothing else. Let's go to the discussion. Nacho.
Just to promote the discussion, I would avoid the use of alternative here when you mean alternative model, because alternative implies that there is something as good as the one as good as the other. No, I think I can use this or this because they are good, so they are alternative. So alternative means something as developed as the standard model. So I found very interesting that one of those alternative models, one of the most developed, at the end it turns out being very similar or very much approaching to the standard model. So that means that, at least in my opinion, it's telling us something important. So when you take into account observational facts, if you want to put this into a framework, whatever path you take, you finish with some scheme that resembles very much what we have right now. So all the ideas that you have presented now need some exotic physics, some physics beyond what we know. I think this is also a very interesting thing to discuss. So we really are missing something still.
Yes.
In my opinion, the dark energy is also exotic, right? In fact,
something that hasn't been discussed about dark energy. Dark energy as itself, dark energy, it would be some mystery to solve. But if the dark energy finishes in being the cosmological constant, okay, the cosmological constant could be considered like a piece of the how the gravity works, like the gravity constant itself. So it's just simply that the law of gravity has two parameters, or two constants, like the famous Newtonian constant, the G, plus the lambda, but would be also a constant. And it would just simply be how the nature behaves, so how the gravity behaves. So it would be a force of the nature with two constants. So you can wonder why is that like that and not differently, but it would be just simply like that. No? So it would be not a mystery, it would be how the nature is.
I don't know, but isn't it like a repulsive force? This is another thing I question myself. I don't know about this. I'm just thinking like all these people working in string theory and all that, trying to fit like 4 forces into one theory. And now if it comes also the dark energy, like to me it would be like one more force to fit or something like that. I was wondering too, I don't know about this, if there are people working, like when we talk about cosmology, it's always like a general relativity or things like that with just the gravity. And I was wondering if there are some people working in like together this putting all forces together and also trying to explain the universe at the same time, because it's like in this theory of everything, you are trying to explain everything. So it would be like if it explains everything, to me it will also explain the universe. No? I don't know if there is such a theory.
I'm not sure whether I understand your question. As I said before, there are people who work in another frame different from relativity. So general relativity is the most accepted frame, but there are other proposals of gravity, the whale gravity, or other. Even the idea of ether, which was rejected by Einstein, still people think that there may be an ether in the universe. So there are plenty of ideas, and the most exotic thing you can imagine is there, most of the thing. But now about the unification of the forces, all what I know is about the string theory, the standard works of this. But I don't know anybody working in that.
The other thing for me also like a little bit, because we talk about this, there are many things here that are exotic, in this model, which I of course agree. But there is also like really, to me, when I think deeply about the Big Bang, and not only this dark energy, but also thinking that the whole universe was inside a space smaller than an atom, like it's a very, 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 very strong claim. I mean, it's of course it's our best theory, but it's still mind blowing. You have to accept it. It's mind blowing, no?
I think so, but we are used to this exotic idea, so now it does not look exotic, but in the moment it was proposed, I suppose it was as exotic as these ideas. So,
I just want to make a comment that normally, I mean, people consider that the universe as a whole just was born in a dot, or I don't know how to say, just in a point, no? In the space. But we should take into account the following. So when we are talking about the universe, we are always talking about the universe that we observe. Okay? So we don't really know about what is the real size of the universe, or even if beyond our observational limits, the universe is explained with the same characteristics that we have so far. So from the philosophical point of view, we are assuming that the sphere of knowledge that we have of the universe extends to the rest of the universe. So the universe could be extremely large, or just simply finish just a little bit farther away than what we can observe. We don't know anything about that. So what we can say is that what the theory tell us is that the universe that we observe is compatible with being born in a really small portion of space. But if the universe is infinite, for example, then the Big Bang took place in an infinite space also. Okay, so this is an important and to clarify.
In this, it is the preferred model that nowadays, the flat universe assumes that we have an infinite space. So, no, you are right that there was a state of maximum density. Of course, the atoms were together with a very high density, as the singularity, but the full space was not a finite space, what Nacho says. It can be an infinite space, even in the beginning of the universe. You want to say something?
I think that almost everything that I could imagine has been already said by you both.
You have been in the course, so you already know Nacho and me. Yeah.
I could, or I would ask you to add something from a philosophical point of view. I think that could be interesting to be introduced here in this discussion. I don't know if it is feasible at all, but for example, something that I think is relevant is the last thing you have mentioned. We are trying to make theories of everything, but observing what is no more than a very tiny part of the of everything. So we are observing just the known universe. If the universe is, in fact, infinite, we are observing almost nothing, and we are making a theory of everything from that. And we may be completely wrong, both in the standard theories and in the more exotical one. I don't know what do you think about this.
My own philosophy is to be general skeptical and to be humble. So I think this is too arrogant to think that we have the model of everything and the whole history of the universe. It's very early. In this, cosmology has begun 90 years ago with Einstein, and I think there is much to run still in the future. If we are able, my impression is that we are not trying to understand a star or a galaxy or a planet. This is something that we can do as physicists. But understand the whole of the existence is something very ambitious, in my opinion. So if you ask me, which is my favorite model, I have not any favorite model. I think all of them have problems. The best one is the Big Bang because it was more elaborated, but surely they will have problems for a long time because I am skeptical. This is my philosophy. But there are three positions. There is the dogmatic position in favor of Big Bang, the dogmatic position in favor of other theories. For instance, Hoyle believing that his model was correct, of course, and then you can be skeptical of everything. You can say, well, let's do this is a game. Let's see what these people do, but do not believe everything. Just just a frame, as Nacho say, this is a frame to fit our observations, and we can do something like Ptolomeo did in his time. But to think that this is the absolute truth of the whole universe, this is too much from a philosophical point of view.
Yeah, I want to point out that in fact, if we just, so at the end we will make a cosmological model of just the part that we know, or the part that we can approach with the telescopes and with our observational limits. So we will always remain with the doubt whether this is the explanation of the rest of the universe or not. So I would just simply, but this is something new in the history, I would have to say. And it's very interesting. I think we live in a unique time in terms of cosmological models compared to the past or previous people. Is that we know that even our most elaborated model, able to explain all of the observational facts, we will always remain as a provisionary one, just simply due to we know our own limits in terms of observations. So I think this is very, very important from the philosophical point of view.